All right, here's a video about compound angles or compound bevels, technically, right? It could be used for miters too, but so this is a hip cut or a cheek cut, and there you go. It's a face cut to, let's say it's to it's a little, it's an inside hip, right? It's an inside hip cut. And if you want to cut these on a horizontal bandsaw that doesn't tilt, you can. You just gotta know how to put it in the saw. Technically, usually it's gonna be with the jig, but you could make a, well, anyways, you have to jig it up to rotate it on while it's being fed in, and then there's a dihedral cut. So I'm gonna go through quickly kind of the steps. It's a big mess, but you have to find the dihedral angle, which is this angle here. I'll draw it in something that's not mucked up. So this was the test to make sure that they worked. You put them in there, you rotate them, and then this dihedral cut, and then you cut them, and then you pasted them in there, and then they were perfect. Let's see, from there it would be the plan view would be right there. So see how they're just perfect, right? And that's actually with decimal measurements of the box that has a little error. So if you zoomed way in, you might see a tiny little error. Yeah, I see it. Maybe it's a, let's see, right there from there. You're still getting a zero distance, right? And I think I'm on 5 or 6 decimal places. So yeah, so it's within the 10,000ths, right? But if it was actually done with the box, it was precision size and cut, and that would probably fit. It would fit in there exactly. I think using Excel goes to 15 decimal places, and then that's what this is all about. So this is the formulas, right? Degrees, arctangent, square root of this, and over this, and that gives you the angle, the dihedral angle, right? So it was square root of this, and this over B7, which is, let's take these out of there. So V, this is the angle we're looking for right here, delta MA. So that's the angle. And it's 49.33. And this is the width, right? And that's the height. So it's the square root of this squared plus this squared divided by the depth, which is 20.073. That's weird. I think I just copied and pasted that box, and it's 20.916 over here. Alright, so let's see. That's actually just kind of weird. But, and then 21.937. Oh, because I scaled the box up just to make it so that the pieces that I just picked an arbitrary, technically that's called a parallelepiped, but a solid, 2x or something, right? And in this case, it's a solid, I don't know, it was like 5x5 maybe. All right, so there's the one angle. That's the dihedral angle. That's the one you're going to set it on the table. That's the setting the table angle. And then here, this is, you could probably find calculations for this on the internet if you type in backing angle. But this angle right here, this red angle, 27.77 or 27.78. You just got to go through and you find you have the plan angle, right? The width divided by the depth, and then you have that, and then you have the angle of the rise here, right? And then you have this triangle here, so the plan angle. So this base of this dihedral angle, let me zoom in a little bit. The base of this dihedral angle is X, So x over the depth, which is 20.916, is the sine of the plan angle 39, right? So let's just go through and look at that real quick. So we're looking at base of the rotation, right? Plan angle, and then base of the rotation, x over the 21.916, and then if you solve for x, you get sine of the base angle times 20.916. So it's all that back, just going around and picking up this rise of the rotation angle the same way. You have the pitch, the plumb cut angle or the vertical angle, and you have the same leg here. This would be x over 20.916 be the cosine of the plan angle, and we solve for this, and then you have this plumb cut angle. The one we're looking for is x over the diagonal, which would be the sine of that. It's 7058, so that's kind of the same thing. Looking for rise of the rotation angle, sine of the radians, sine of the plumb cut times B13, which was B13, base of the plumb cut angle. Oh yeah, because we had solved for that, so we're just using it. Could have used the depth again, right? Instead of using the sine, could have used the cosine, but that would have been this angle. Anyways, there's just where you just go through, do the whole bit back and forth. Say, you know, this is my rough. Here's the rough, kind of looking at what do I got to do. Did a little bit more explaining. So when I come back and I lose track, I can kind of see what the calculation I'm doing is. You get through that all the way to the end, and then, you know, in this modeling program, you can take the piece, you put that angle on there, Alt MA. .39, 46.39, right? That's the angle there. And the rotation, Alt MA. It takes a little practice to figure out which ones go where. 27.777. Right there. 27. Rotation, 27.777. So the first one is the answer you're looking for. The last one's the answer you're looking for. It's like I said, you just go through and do all your calculations, figure out your sides, your lengths, so you can get the angles. And that's it. So I don't know if that'll ever help you in your career, but it's helped me on quite a few where we're cutting big tubes and beams by hand, and the saw was big enough to handle some of them, so we were able to put them in the saw. When we made the order for our templates, we had the angle put up on the templates, so we made a couple of those and welded them or tacked them to the table and cut all the rights, and then took those, flipped them around, and cut all the lefts because they were the same. They were at 45 degrees, and fed it from the other direction. So it was doable, and it was a challenge. It was kind of cool. And I figured I'd share that it's possible if you ever want to cut compound angle on a non-tilting bandsaw. Good luck.